So we just saw that a simple sort algorithm, like selection sort, is too expensive. It's quadratic, and that says it's probably going to outweigh the advantages of doing a logarithmic search using binary search when we're done. We're probably better off using linear. But we'd really like to say, gee, isn't there a better way of doing this? And we said earlier on in this lecture that we look to reduce problems to known solutions that we can leverage. And in fact, there is a better way of doing this sort, and it takes advantage of another technique we saw. So the better version of sort is called merge sort. And it uses a divide and conquer kind of approach. So what does divide and conquer say? It says break it down into smaller versions of the same problem. And here's the basic idea. If the list is of length 0 or 1, I'm done. It's already sorted. But if it's bigger than 1, let's just split the list into two parts, and let's sort each one of those. And of course, those may involve some additional splits. But if I can do that, if I could sort each of the sublists, and I assume I can do that faster than sorting an overall list, then I'm going to merge the results. And the merge takes advantage of the fact that the two lists are sorted. To merge, I'm just going to look at the first element of each list and take the smaller one and move it to the end of the result. And keep doing that until one of the lists is empty, in which case I just copy the rest of the list onto the end of the result. So another way of saying it is, given two sorted lists, I'm always picking off the smallest element and adding it into the new list that I'm creating. And I can do that, we hope, quite efficiently. Okay, with that in mind, let's just look at an idea of this, and then we'll look at writing the code for it. So the idea of merging is, again, as I said, I'm going to start off with, let's look at two lists. Let's imagine that I've got two lists here that have been sorted, and I want to merge them together. Okay, I'm going to worry separately about how I sort them, although that's obviously just going to be a recursive version of the same thing. And here's where I am, right? If I've got two lists here, I'm going to take the smallest or first element of each one. I'm going to do that comparison. And I'm going to take the smallest one of those and move it into the result. Okay, and when I do that, okay, now, again, I've taken that one off of that first list. I've still got two sorted lists. Again, I take the first element of each. I'm going to do that comparison. And I'm going to take the smallest one and move that into the result. And now you can see I can continue that at each stage. And by the way, in that case, I removed this one from that list. So each stage, I'm simply taking the first element of each, looking at the smallest one, adding it into the result, taking the first element of each, taking the smallest one, adding it into the result, taking the first element of each, taking the smallest one, and I keep walking through that stage until I get to the point where one of the lists is empty. And at that point, I simply copy this entire list onto the end of that list. So you notice now, because these lists are sorted, I'm not looking at everything in them. I know that the smallest element is at the front. So the merging step actually works quite nicely. Okay, if that's the case, let's now look at what's the complexity of this algorithm. Right, doing the comparison, that's constant. Doing the copying, that's constant. So all I really have to ask is, so how many comparisons do I do? If the combination of the two lengths of the list is order L, I've got to do at most L comparisons because I've simply got to look at each element until I've merged them in. In terms of the number of copies, well, that's order of the length of L1 and the length of L2, or the length of L overall, if you like. So in fact, merging is linear in the length of the list. Cool. It says I can merge things in an amount of time that's linear in the length of the list. Okay, with that in mind, let's put this together. So here's now code to do the merge. And it's really pretty straightforward. Right, I'm going to set up a result up here. I've got two indices, I and j. And while they're both less than the end of each of their respective lists, I'm just going to compare using some comparison operator. It could be less than. I'm going to compare the two of them. And I'm going to basically say, if the left one is less than the right one, I'm going to add it in and increase I. Otherwise, the right one's the one I want. I'm going to add it in, and I'm going to increase j. Oh, that's nice. That's basically saying the equivalent of me removing things from the list. I'm simply changing where I am in either the left list or the right list. When I get to the point where I'm almost done, I'm going to check it. And to see that, I'm going to say as long as I is less than the length, sorry, I'm saying this poorly. Up here, I've got both of them still have something in them. When that's no longer true, if there's still stuff left in the left one, I'll add them in. Otherwise, I know if there's still stuff left in the right one, I'll add them in, and I'm going to return the list. So this is just a piece of code that captures that idea of merging. It says basically, let me do the merge by walking down each of the lists, doing the comparison to see which one's smaller, adding it into the result, and changing that index. And when I've gotten to the case where one of the lists is empty, I'll simply add in the remainder of whichever list still has things in them. Okay, we can now put this together to create a merge sort algorithm. And that is going to be something that's going to do sorting by breaking down the lists into sublists, sorting each one of those, and then merging the results together using the merge operation. So what does it say? It says if I got a list of length 0 or 1, just return a copy of that list. Notice what I'm doing here, by the way, I should have said, is I'm using the operator function of less than to set up something that's going to do the comparison. So I'm going to use a typical less than, and this says I can pass in, if I want to, some other argument for compare. The default's just to use the standard less than operation. All right, if the list is of length 0 or 1, I'm done. Otherwise, what do? Well, it's really cool. I compute the midpoint by basically taking the length of the list divided by 2 and making sure I get an integer back out. And then I take the lower half of the list, and I do merge sort on that. I take the upper half of the list, and I do merge sort on that. And that says, oh yes, recursively, I'm going to keep doing merge sort on these. I know by the fact that I keep breaking it down into a smaller version of the same problem that when this is done, it's going to give me back sorted lists. And having sorted the left and right versions, I simply merge the two, and that gives me back out the solution I want. Cool. It says I've recursively broken this down so that I do a merge sort on the smaller versions of each of the two lists, and that will keep doing it until I get to things that I'm just merging lists of length 0 or 1. When I'm done with all of that, I do the merge of the overall thing, and I'm set. Okay, now, what's the complexity? Well, we know that the complexity of merge is order of the length of the list. We just argued that earlier. It says if I got two lists the sum of their lengths is of length L, I've got to walk through each one of them at least once to do the merge, but no more than once, so the merge is of order length of L. So merge is linear. What's merge sort? Well, it's going to be a combination of a linear in the length of the list times the number of calls to merge. Right? We just saw that with merge sort. We have to go through the list to do merge sort on the two sublists twice. Okay, so we're doing a merge sort on two sublists. How many times do we call merge? Well, that's the same as the order of the length of the list times the number of calls to merge sort. And what's that? Well, we just saw that that was logarithmic because we're breaking it down in half at each stage. So this is just a combination of the length of the list times the log of the length of the list. And that says that this is log linear, which is actually fantastic. It's order n log n, where n is the length of the list. And that really does say, fantastic. I've gotten now a very efficient algorithm, an n log n algorithm. Should note, it does come with a little bit of a cost, and the cost is in space, as it has to make a new copy of the list, but other than that, it's really very cool. And that's wonderful.